Hi, welcome to Dissolved Chemistry. Let us continue our discussion on this equilibrium. In the previous video, we have initiated our discussion on this chemical equilibrium, where we spoke about what equilibrium means and the dynamic nature of the equilibrium. And apart from that, we have discussed regarding what would be the equilibrium conditions when we reverse the reaction, that is, if we start the reaction with the products. So now in this particular video, we are going to discuss regarding law of chemical equilibrium. Okay, so prior to going for that, we know that when the reaction attains an equilibrium, say for example A plus B combines to give C plus D. Okay, stoichiometric coefficient, we will take it as A, B, C, and this we will take it as D. Okay, so now at equilibrium, what happens? At equilibrium, the net change in the concentration of the product and reactant is going to be what? 0, or it is not going to change, or the constancy in the concentration or in the pressure, if the reactants and products are the gaseous, indicates what? The state of equilibrium. Okay, so prior to that reaching of the equilibrium, the rate of forward reaction, which is greater than the rate of backward reaction, therefore the reaction is progressing in the forward direction. There is a continuous change in the concentration of the reactants as well as the product is observed. As soon as it attains an equilibrium, so then there is no net change in the concentration of the reactants as well as product. Okay, so now this law of chemical equilibrium, we are going to derive it by using law of mass action. According to law of mass action, okay, according to law of mass action, what we see is that for a given reaction, rate of chemical reaction is directly proportional to active masses of the reactants. Here we are assuming active masses as molar concentration we are assuming. So therefore rate we are going to define as RF, I will write because it is an reversible reaction. Rate of forward reaction is directly proportional to product of molar concentration of the reactants, where the stoichiometric coefficients are raised to the power. Okay, similarly, as it at equilibrium, so there is a what we call backward reaction also we are going to find. Reversibilities, backward reaction is also there. So therefore a rate of backward reaction according to law of mass action, what we can give is rate of reverse reaction is directly proportional to product of molar concentration of the C and D we are going to observe. Okay, now as we know that at equilibrium, okay, RF, rate of forward reaction. Okay, we will remove this proportionality sign first. Proportionality constant, we call it as what? Kf is being introduced. Okay, similarly for reverse reaction, we give R reverse is equal to Kr into C raised to the power C, D raised to the power D. Okay, so now at equilibrium, right, we know that rate of forward reaction is equal to rate of a reverse reaction or backward reaction. So therefore when these two becomes equal means what? Kf is equal to Kf into A into B, okay, raised to the power B, A you can keep it, is equal to Kr into C raised to the power C, D raised to the power D. where Kf and Kr are the rate constant of forward and reverse reaction. Okay. So now, if you take this constant on one side and these concentration terms on other side, then what we will get? Kf by Kr at equilibrium is equal to molar concentration of the products and divided by molar concentration of the reactants. Okay, so this is how we are going to give. And this we call it as what? Another constant called Kc or K equilibrium we are going to call. And this K equilibrium is nothing but what? The equilibrium constant. Okay. The rate constant of both forward reaction and backward reaction ratio, we call it as what? Equilibrium constant. Okay, equilibrium constant. And this equation we call it as what? Law of chemical equilibrium. Okay, so now let us define this term. What is this? It is the product of concentration of the products where stoichiometric coefficients were raised to the power, individual powers, okay, divided by product of molar concentration of the reactants where stoichiometric coefficients were individually raised to the power. Okay, so that we will define, right? Law of chemical equilibrium. Here it is equilibrium constant, which is the ratio of rate constant for forward reaction to the rate constant to the reverse or backward reaction. Okay. Or in simple terms, how we define the product of molar concentration of the products to the product of molar concentration of the reactants. Always it is equals to a constant, or you will be getting a constant value, and that constant value is nothing but your equilibrium constant, and this we define it as what? Law of chemical equilibrium. Okay, so now this is the how we are going to define when the reaction is as shown, and this we call it as what? Forward reaction, and this we call it as what? Reverse reaction. Okay, or backward reaction, we can use the term called backward reaction. When the reaction which attains equilibrium, if we represent like this, then equilibrium constant we will give as Kc is equal to molar concentration of products, okay, divided by molar concentration of reactants, right? So now, if the same reaction, if we start with by taking products, okay, and if we begin the reaction, okay, instead of starting with this, if we start with this, means if we reverse the reaction, meaning is what? Instead of taking A and B in the reaction vessel, if you take C and D and if you start the reaction, then what happens to the equilibrium constant? That we will see. C moles of C, okay, plus D moles of D are going to combine to give A moles of A plus B moles of B. Then the equilibrium constant for this we are going to call it as was K dash C, which is equal to A to the power A, B to the power B, because these are the products now. Okay, they are not reactants now, they are products. So therefore, C raised to the power C and D raised to the power D. Then what it implies? This shows that it is equal to 1 by Kc. Okay, if I do reciprocal of equilibrium constant of the forward reaction is nothing but what? Equilibrium constant for the reverse reaction that it implies. Okay, now suppose if I, instead of this, if I multiply the stoichiometric coefficient, means instead of, say for example, A moles, if I take Na moles of A, okay, Nb moles of B to give Nc moles of C and Nd moles of D, then what happens to my equilibrium constant? That we will see. Okay, now suppose Na moles of A plus Nb moles of B were taken to or reacted to give Nc moles of C and Nd moles of D. So then what happens? My equilibrium constant will be given as what? K double dash C is equal to Kc raised to the power n. Okay. So these are the three important relation one should remember. Okay. So this is for the forward reaction. This is for the reverse reaction. And if we multiply with the stoichiometric coefficient. So this I will illustrate with one example. You take, say, for example, for H2 plus I2, okay, to give 2HI, okay. So then the equilibrium constant Kc will be given as what? Hi raised to the power 2 divided by H2 raised to the power 1, I2 raised to the power 1 we will give. So the same, if I multiply this, if I take half mole of H2, half mole of I2 to give 1 mole of Hi, then how it would be? H2 plus half mole of I2, okay, so then it will give 1 mole of Hi, and we will give this equilibrium constant as K double dash C, okay, which is equal to what? So how we will give? See here. So you will be getting Hi divided by S2 raised to the power half and I2 raised to the power half. And that is nothing but what? Kc raised to the power n. Okay. So where n stands for what? Stoichiometric coefficient, the multiple of the stoichiometric coefficient n we can call. Okay. Kc raised to the power n, you should remember. These are the three important relations you should remember with respect to the equilibrium constant. Okay. The next we will talk about types of equilibrium, that is homogeneous and heterogeneous equilibrium, in upcoming video. Please don't forget to subscribe our channel. Okay. And thank you for watching.